Hi guys, welcome to today's video in which we're going to be looking at the next method we have for examining how energy is distributed around the Earth from areas of solar surplus to areas of deficit. And what we're going to be looking at today is oceanic circulation. Now, before we get too deep into this, we first need to consider why is there a difference between heating up areas of land and heating up areas of water. Now, if we think about the oceans first, as we heat them, as we apply solar insulation to them, one of the first things that we need to bear in mind is that water is transparent. That means this energy can penetrate the water to depth, and it heats it to depth. So it's doing a lot more work. Now, because that's happening, because the water's being heated differently at different depths, we get convection. Water moves. So this further moves the energy around in the water. We've also then got evaporation. Water, as it's heated, will evaporate, and that moves it away from that part of the system. If we think about land, we've got none of these things. Land gets heated, and it's only the very topmost layer of the land that actually gets heated. Because, well, if land started to spontaneously mix or evaporate, that would be absolutely terrifying. But because of this, the energy in the oceans can move, and it can move around, and we don't get that with areas of land. Now, what does this mean? How are we going to actually use this, and how are we going to talk about it? Now, first, if we have a look at this map of the world with loads and loads of lines on it, and the first time you look at it, it can be really confusing looking. We are looking here at a map of all of the major oceanic currents around the world. Now, one of the first things that will hopefully jump out at you is there's lots and lots of different loops on the map, and we call these loops gyres. Now, these oceanic gyres are areas where we have got water transferring energy from the tropics, from equatorial regions to the poles, and to areas where we've got colder water. Now, a couple of things that we know about how water moves. Generally, it's driven by winds, it's driven by these convection currents. We got a lot of work done by the prevailing winds. So particularly, if you look at the situation in the Atlantic here, if we remember back to the previous video, when we were looking at some of the winds that are driven by the three-cell model, we can see that these currents, are moving in the same kinds of direction. You know, here we've got currents moving vaguely in the directions of the trade winds. Here we've got currents moving vaguely in the direction of the kind of predominant westerlies that occur in these areas. Now, because of that, the water's going to move until it runs into something like a continent, which is fairly hard to move if you're a stream of water. So when the water hits the continents, it gets deflected. And once it gets deflected, it keeps moving until it bumps into something else. Be that another landmass, be that an area of colder water, warmer water, or be that a different prevailing wind system. Now, what we're going to look at and what we're going to focus on for the majority of today's video is going to be the North and South Atlantic gyres, and we're going to look at how that system works. Now, this is our diagram, and it is equally simple and confusing at the same time. So what I want to do is we're going to strip away most of the arrows, and we're going to go through this one little bit at a time. Now, if we start with this, we have got our convection currents at the equator, and thanks to the trade winds, we see that we get two equatorial currents, north and south of the equator. And this drives warm water from Europe and Africa across towards the Americas. Now, when it gets there, it gets deflected. Now, most of the water goes north in the northern hemisphere, south in the southern hemisphere. But to just tie up a little bit here, some of the water goes south in the northern hemisphere and north on the southern hemisphere. And you can see that we've got these two little currents that they come up towards each other, they hit, and then they go back across the equator in north or south again. And we call this the counter-equatorial current. Now, our main two bodies of water, they move, as I say, north in the northern hemisphere and south in the southern hemisphere. And what we've got is the Gulf Stream and the Brazilian currents. And this is still warm water. This is the first of our big batch of warm water that's moving north or south from the equator to the poles to distribute energy to either of those two areas. Once we get there, we start to see the westerlies take a big influence over both of those. Now, in the northern hemisphere, the water actually stays quite warm, and we get the North Atlantic drift. Now, we're really familiar with that here in this country because it goes a long way to explaining why the climate in Britain is, largely speaking, a lot nicer than it should be given our latitude. And that's in no small part down to this warm area of water that we have coming across. In the southern hemisphere, it's a little bit different. You'll see another sneaky blue arrow has appeared here. We'll talk about him in a minute. But the water goes cold in the southern hemisphere and it forms something called the west wind drift. Now, both of these currents, they travel across the Atlantic Ocean and they bump into Europe and to Africa. When they bump into that, some of them go south in the southern hemisphere and north in the northern hemisphere. In the northern hemisphere, it goes north up towards Scandinavia, up towards the Arctic. And in the southern hemisphere, it goes down round South Africa towards the Indian Ocean and around Antarctica. But the ones that we are looking at in our gyres. So, we've got cold water now. Most of the energy that even in the northern hemisphere, that the water had, the heat that it still had, has gone and it's been replaced by colder, more dense water. Now that comes south as the Canaries current, and it goes north as the Benguela current. And that nearly wraps up our two gyres, our two loops. Now we've got one thing left to add in. Both, you see I had this little arrow down here earlier, and I've added one up at the top as well. Around about between 40 to 60, 70 degrees north, we have other currents that sneak in. Now in the northern hemisphere we call this the Labrador current. And its name's associated with Labrador in Canada, because that's where that current comes from. And it brings some cold water down. Now because this cold water is more dense than the warm water it's coming into, it helps to drive this system. And similarly, down here with the Falkland current, again, named with the Falkland Islands that it passes by, it's cold, it's very dense, and it helps to move some of this warm water on and across the Atlantic. Now, what you're expected to be able to do is to basically talk through this diagram. This is one of the few diagrams in Higher where I would expect you to be able to draw it from memory. And it's why I tend to keep it as simple as I can and blocky, and it tends to be quite straightforward to draw. Where it becomes confusing is once I put all the labels back on. Now, this is a really busy clutter diagram. Now, please bear in mind that obviously on my screen, it's not ideal. I slapped this together reasonably quickly in PowerPoint. But I do encourage you guys, take a little bit of time, draw this diagram out. Keep the continents nice and blocky and simple, but take some time with your arrows, with the labels. Make sure that you can identify which label attaches to which oceanic current, okay? And if you need to go back through this little section of the video to get that, please do. Now, what is the kind of purpose of this? What effect does this have on climate? Now, warm currents make areas warmer, and they make, well, obviously because they are warm, and they increase rainfall. So if wind blows over a warm current, the heat from the water makes the air warmer, hence it increases temperature. It also means that the air can absorb some of the moisture, we get some evaporation. Now that then blows onto coastal areas and it makes them wetter. Now, really common examples of this are places like, Rio de Janeiro, where we've got the warm Brazilian current offshore. The prevailing winds blow warm, wet air onshore, and it makes the area warm and it makes the area wet. What about the other side? What about if we've got cold currents? Now, they do the opposite. They make areas colder and they make areas drier. So similarly, wind blows over a cold area, that reduces the temperature of the air, making it colder. Also, not much of that moisture can get evaporated. We don't have the energy, we don't have the heat to actually evaporate it up. And kind of worse than that, it might be condensed down into fog and even suck moisture out of the air. And then when that air finally moves inland, the fog that it may have formed kind of burns off and the air has got no moisture in it. So some of the impacts we see of this, all of the world's hot deserts, for instance, have got cold currents on their western side. Have a look through the world map and you'll see it. The Sahara Desert has got the Benguela current. The Atacama Desert has got a current on the, and I forget the name of the current, that runs up the other side of South America. But it's a cold water current. It's similar in Western Australia, places like this. They all have these cold currents. One of the good sides of the cold currents, however, is a cold current does encourage a lot of mixing in the water column. Because if cold water comes in and it hits warm water, the cold water is much less dense, so it wants to sink. Now that sinking and that mixing kicks up a lot of material that we can have throughout the water column, and it creates food for fish. And it's why we see, so South Africa and Peru are a couple of the examples we have here, where fishing is a really important industry, because this kicking up all of the different material that was in the water column that's along the coastline creates fish food. It creates nutrients for fish to eat. Thus, it makes the area more heavily populated with fish. Now, that wraps us up today, guys. So in today's video, we looked at ocean currents, ocean circulation, and how oceans can help to distribute energy from the areas of surplus at the equator to areas of deficit at the poles. What we're going to move on to in the next video is we're going to be looking at the intertropical convergence zone, and that's going to involve looking at how the thermal equator can move north and south throughout the year, and the impact that can have particularly on Africa with bringing rain to various regions. And until then, I'll see you guys next time.